just make a small discussion on the thoughts, the engineering thoughts of water tanks from a perspective of the material of construction. Because when we look at the material of construction and we start thinking of the engineering considerations, then where we can place them also comes in as part of that, of those engineering considerations. So I'll start with masonry tanks. These tanks can be placed on the ground or underground. These tanks can be placed on the ground or underground. On the ground or underground. Of course, to make the water tanks watertight, you want to have good quality blocks of low porosity. Need or require good quality of low porosity. These tanks, once they're built, they need to be plastered with waterproof. Both inside and outside if possible. Masonry will usually be built with hoop iron. The masonry hoop iron or small size reinforcement, like 8mm diameter bars, T8, every or every alternate level, every 2 causes. The preferred shape for this tank is circular. Since this shape is efficient in carrying radial stresses. Okay, best way is to think about this in terms of like the egg. Is it the duck egg or the chicken egg? There's a direction in which if you hold it and try to break it with your hand, it is next to impossible to break it. Why? Because the shape has been optimized such that it carries the externally applied stresses almost purely by compression, and that makes it very efficient. You find a very thin element that you require a lot of force to just be able to break that shell in that particular direction. So I will not go into too much detail about it. So these are the thoughts that would be considered for the masonry tank. Reinforced concrete tank. These tanks are very versatile. You can do them any size, any shape. You can do them as underground tanks. You can put them on the ground. You can put them as elevated. The options are just limitless concerning these tanks. You can have them rectangular. You can have them circular. You can have them conical shape, etc., etc. It's a whole array of possibilities with reinforced concrete tanks. That is, you can have any shape. You can put them underground. You can put them on the ground. You can have them elevated. You can have them any size, from pretty small ones to etc. These tanks are made of reinforced concrete. Therefore, they require a good design. Reinforced concrete design. Okay, and usually you design for the ultimate failure, and also serviceability is very important for this one. Especially cracking. If time allows, and I hope it does, we will look at how we calculate, how we check cracking sizes in concrete. So, of course, you need a good material. You need a good concrete mix. You need a good waterproofing to go with the concrete mix. You need to have a good particle size distribution for the aggregates that you're putting into the mix so that you have a good packing density. You need to have, the concrete has got to be properly mixed. The concrete has got to be properly placed and compacted so that you do not have too much voids. So you need good quality material. That is, you need good concrete mix, good aggregate, and particle size distribution. You need to put in waterproofing. You need to have it well placed and compacted. And all that goes into making good concrete. So as I've said, you need to have good construction. Okay, so you've got to have good compaction. You need to have good curing. A lot of times we also prefer that this we do plastering on this of these concrete walls with waterproofing cement. And of course, you could also work with the pozzolanic cement, because the pozzolanic cement over time, because it continues to react. The pozzolan in the cement continues to react, and therefore continues to fill in the pores. And with time, it has a good sealing. The third one, which has become very popular, is plastic water tanks. This is the most popular currently. It's also the most versatile. As you know, you can do this to any size, to any shape. You can place these tanks underground, like what Rototanks has done. You know, they've done these spherical tanks that you bury underground. You can have them on the ground, you know, on a plinth, or you can have them elevated. You can have them on a water tower or water tank tower, or you can have them on a roof slab. You know, you can place them all over the place, any size, any shape. Okay. These can be placed anywhere. They can be any size. They can be any shape. These tanks require protection from the sun. Though this problem has been dealt with quite a lot and aggressively from a materials science point of view, plastic generally gets deteriorates when it's exposed to infrared light from the sun or from any other source. And so, therefore, whenever you have this kind of tanks, you might want to consider whenever you're specifying this kind of tanks, you might want to consider providing some nominal protection from direct sunlight. Maybe you might not have noticed this, but when the plastics started becoming common here in Kenya some years back, if you left your bucket or your basin outside in the sun, after a while it would start peeling off. You know, some layers will start peeling off. And that was partly a result of the exposure to infrared, ultraviolet, sorry, not infrared, but ultraviolet. UV is a problem. Ultraviolet. Okay, so you might want to protect them. The other important thing for one as a designer when you're specifying is that you need to know that the quality of these tanks varies. The quality from one manufacturer to another. And therefore, one has to check quality carefully. I'll give just an indication that you could be buying, say, these huge tanks. You find one manufacturer sells it to you for what? Maybe 80K. Another manufacturer sells it to you for 65. Something must be significantly different for them to be able to sell at these two prices. One of the differences is the thickness of the walls of the tank. Manufacturers are very, very smart people, so they know how to play with the thicknesses to save on material. I once got to do some factory buildings for one of the leading plastic container manufacturers here in Kenya. So he was actually doing a second factory, or a third factory or something. And he took us through his manufacturing process and was showing us these simple containers, these 20-liter is it 20 liter or 5 liter? I think 25 liter or something, or 20 liter, I can't remember. These containers, the ones that they put mafuta, or they put, those ones, the yellow ones. He was telling us, traditionally they have used about a kilo of material of plastic to produce those, but now they have found that the walls of the container carry loading mainly by tension, so you don't need a lot of cross-sectional area. So they reduced the thickness of the container, and effectively from 1,000 grams of material per container, now they were able to work with 900 grams. So from 1 kilo, they reduced the material to 0.9 kilos, and they do this a lot. And if you touch the container on the side, you actually feel that it's a bit lighter than the other container that is done with a kilo material. And this they do a lot, and you can imagine if they can save 10%, on such a small container. How about a container that has maybe 50 kilos worth of materials? And they save 10%. That's 5 kilos of material they have saved, and I will. So every 9 containers, they have one container extra, and they do this a lot to try and beat the competition, because again, that's a competitive area of manufacturing. So you as the designer needs to be keen on the quality of whatever you're providing. Of course, the other thing is that the quality of the plastic material itself could vary. Now, this is difficult to check or to test, but good quality products speak for themselves in the market. So you can just ask or check what has been installed, how long it has been there, and what kind of problems it has brought, and then you start feeling the leaning towards a particular manufacturer because their products perform better. So these are the basic thoughts of these tanks. Of course, if these tanks have to be underground, then the shape of the tank, the most sensible is spherical, because of the obvious advantage of the efficiency of carrying stresses, because now then it carries stresses from, when it's empty, it carries pressure from outside, and these stresses, if it's spherical, most of them are carried in compression. Okay, then we go to the pressed panel steel tanks. 4, pressed panel steel tanks. Pressed panel steel tanks. These tanks basically modular. They come in square panels. Either 1 meter by 1 meter or 1.22 meter by 1.22 meter, I think, if I can remember properly. So what happens is that these steel plates, very thin, maybe 2 millimeter thick plates. You got those steel plates. Let me draw 2 panels, so that we can. I'll explain everything. I'll try to make it clear. So let's say we have 2 panels here. Sketch is not very good, but it will do. Okay, so initially you have a plate like that. It's square. Then you notch it. you cut that one off, that one off, that one off, that one off, and then you fold there. Fold there. Fold there. Fold there. Okay, so fold. Cut off. These parts. These parts. Okay, so when you fold like that, you form a shallow trough. You know, shallow trough. Now, the way this is done, then these troughs are just connected one to the other with bolts. So you put in between the walls of the troughs, you put a sealant. It's called the mastic tape. Mastic tape sealant between the panels. Okay. And of course, these are bolts. So bolts. The plate I've just mentioned, plate is in the range of 2 millimeters thickness, and it's mild steel. Okay. Then at the bottom, these panels, a pattern is usually pressed there. So they wind up with some pattern. Wind up with some pattern like that. Now this pressing of this pattern is basically to stiffen the plate. You see, the plate is just 2 millimeters thick, and it's, you know, it's say 1 meter by 1 meter. So it's really, you know, flexible. So this pattern is pressed here to make the plate pattern is pressed onto the steel sheet, give it some stiffness. Okay, now I want, when you after this class, when you go and look at the elevated water tanks, the steel ones, you're able to see these features. You're able to see the pressed panels. You're able to see the bolts, literally. You're able to see the pressed pattern, and you know, when you look at this, you should be able to then know why they're doing that. So because these tanks are modular, so if you need a 1 cubic meter tank, for example, you just pick 6 panels of 1 meter by 1 meter. You carry them to site. You can load them onto a pickup truck. You carry them to site, and you just with the masking tape, mastic sealant, tape, you put in between, you bolt, and you have a tank. So that's the biggest advantage of these tanks, that you are able to prefabricate these panels in the yard. You know, if you have a fabrication yard or something, you can prefabricate these panels. You can have them in storage. So if somebody needs a 25 cubic meter tank, you know, it's 5 meters by 5 meters by 1 meter. So you just count the number of panels, you load them onto a pickup. They are not bulky. You load them into a pickup, you can take them to any part of the world, literally, you know, way out of town, and then you just need to then go and assemble it, and you have a tank. So that's one of the biggest advantages of these tanks, and they're pretty popular. Of course, if you need to build them in places where in places where you have corrosion, then you might even need to want to protect, may need, let me write this, may need to protect the panels against corrosion if being put up in aggressive environments. G by zinc coating, galvanizing, etc. But they're very good, reliable tanks. We've said that this tank is fairly versatile. If you put this tank on the ground, you have to provide a plinth. So that the tank is raised, is removed from the ground, because if it is placed on the ground, of course, then corrosion will occur quickly. These tanks, however, cannot be put underground. Because of issues of corrosion. Challenges. Most of the times you find that these tanks are elevated, usually. I am almost certain that within campus here, we must be having a few of these tanks elevated. You guys, you know this campus better, you know the corners better. I'm almost certain that there's some elevated water tanks somewhere that are basically pressed panel steel tanks. We have said that these tanks are very flexible in terms of size. Since they are modular.
I have a question.
Yes, please.
Okay, the reason we've said they're not put underground is because of corrosion issues. How do we take care of the corrosion from the inside of the tank? Because there's actually going to be.
But I've just said that you can protect these using zinc coating, paint or galvanizing or something like that. Didn't I say that just a few minutes ago? If you have a fear that this tank will be exposed to corrosive environments, then you specify, maybe some zinc paint as a finishing coat, or hot dip galvanizing. But hot dip galvanizing is very expensive. It could easily double the cost of the project by just that specification. So this, sometimes maybe you're providing this tank to some remote area, they have a borehole, the water is salty. So then automatically the issue of corrosion arises. So then you have to make provision or specification to be able to answer to that problem. These are fabricated. I'm trying to rush a bit in a factory. Only taken to site for assembly. So you you see the obvious advantage that, you see, at the factory, if you're making anything in a factory setting, the quality control is much better than if you're trying to do this in some remote site. So you've got good jigs, you've got good equipment, you've got good rigs for setting up, for bending these, you've got the machines for properly bending these. You know, if you don't get these lines straight, this tank will never seal. This fold has to be straight. Perfect. So one tank was someplace when I was a lot younger. When I started working, I worked for a steel fabricator. Really, serious steel fabricator. And we used to provide a lot of these tanks. So once a tank like that, it was big. I think it was very big tank. So this client came, bought this tank together with the tower. So we designed the tower, it was fabricated, and the tank was, then we packed it and it was taken to site, and it was some far-flung place. I don't know whether it was in Western or it was in Northeastern. So they put in a truck and they went with a few erectors, the people who do the actual erection of this thing on site. So when they finished erecting, then they, of course, when you provide a tank, before handing over, you got to test it. So the water was put in to this tank, and it was serious leakage, and it became a big issue. They tried to change the mastic, so they dismantled, they put some new mastic, they bolted again. What? Eventually, they realized that the problem was some of the panels were not bent correctly. The bent was a bit off, and the fellows who were bending, because they didn't want to be fired in the yard, they didn't say that they had goofed, so they just let them go that way. So eventually, it became a very expensive exercise, because then at the cost of the fabricator, a truck had to go back, pick the tank again, bring it back to site, trial assemble it on site, fill it with water, check what was the cause. That's how this was discovered. And of course, then all the panels that had issues were replaced with good ones, and then it was taken to site and it was okay. So that fold is important, and it's a good thing that these tanks usually are fabricated in the factory, so you're able to control your quality very well. The last item maybe I can mention is that these tanks are very light. Very light. Therefore, the structure holding the tank basically the tank tower is lighter, more economical. So that's a pressed panel steel tank. There is one more tank I want to talk about, is a corrugated iron sheet tank. Now this tank, the popularity has gone down now, but I see if you go to industrial areas, a few installations there, they still have these tanks. So these tanks are not very common nowadays. Mainly due to rusting issues. These tanks will mainly be placed on the ground or above ground. Probably you guys might not have an experience with this, but I know, for example, that my grandfather had them in his compound, had, you know, for rainwater harvesting. So you'd have a home, and then you'd have for those homesteads that were well developed. My grandfather was a primary school teacher, so his homestead was well developed. You would have a have a plinth. If you're placing that on the ground, and of course each tank will be placed at the corner of the house, and the gutters then would just send the rainwater there, and then you would have a tap or something. So what happened with these tanks is that they took this normal mabati, you know, this corrugated mabati, then they folded it round, and then welded it. Folded it round and welded it. So there was a weld. There was a weld. And of course, it would just come as a tube with a cover. So then you'd place it on the plinth, and then you just cement a bit around. You know, you'd cement it there a bit. The problem with this tank was rusting, and the rusting would start from where the weld was done. So rusting would start there and where the tank is sitting on the ground. And the rusting was so bad that, you know, you'd use this tar, lami. You'd use tar to, you know, cover the holes. Then after about a week, some new holes would occur again, and therefore they were really troublesome tanks. And when the rusting now kicked in proper, the rusting was so much that in one season, you know, a few months, the height of the tank would reduce because the rusting here has eaten a significant chunk of the tank. Okay. We say this is corrugated iron sheet. So, you know, one could could argue that the nowadays we have alu-zinc. We have the mabati that is you know, factory treated alu-zinc, so it's resistant to corrosion. But how about the place where you are welding? How then do you protect that? Unless now you protect that and you also protect the place where this tank sits on the ground. Generally, these tanks have lost popularity because of those rusting issues. You would buy a tank and you'd have it only for a few seasons, and then that would be it. I want to pause here and allow, if somebody has a question, you can ask. A question or a comment you can ask before I go to the next topic, which is cracking. I want to talk a bit about cracking. Because water tanks, they deal with cracks if you design them using a reinforced concrete structure, then cracking becomes an important consideration. Any question, ladies and gentlemen? Great. So I want us to just straight away proceed and look at this subject of cracking, which I find also pretty interesting. So as a way of starting us off, we say Generally, reinforced concrete will always crack. Reinforced concrete will always crack. When you have concrete that is reinforced with normal reinforcement, it will always crack. Now, that doesn't mean that it's not possible to make concrete that does not crack. You can make concrete that does not crack, but it will need to be pre-stressed concrete. So it's possible to make pre-stressed concrete that does not crack. In the design of pre-stressed concrete, most standards allow you to design either for zero crack at the edge where cracking may occur, or to allow for a small cracking to occur. This is pre-stressed concrete. So it's possible to design concrete by pre-stressing it so that it doesn't crack. But when we design reinforced concrete, like the reinforced concrete that was used to build this U-block, this concrete will always crack. So all this concrete is cracking. It's only that the amount of crack is limited to below a certain size of crack. It's only that the size of crack, the amount of cracking is limited to below a certain size, and therefore is acceptable. Let me write those notes first before, so that I don't forget. So we say, generally, reinforced concrete will have some cracks. It is possible to make concrete that does not crack. This will have to, but this would have to be pre-stressed concrete, pre-stressed concrete. The cracking in reinforced concrete is usually limited to some acceptable levels, depending. Let me break the sentence. These levels, these acceptable levels, use even a different color for this one, it's important. These acceptable levels are dictated by the intended use of the concrete element. For example, I think the BS, if we are just limiting cracks in the light of durability considerations, then the crack sizes must not exceed 0.25 millimeters. This is just an example. If the only thought is to say we are checking the cracks and limiting them to this size so that the concrete will be durable. For example, we would do this in bridges, we would do this in box culverts. We would limit the crack size to 0.25 millimeters. So we would calculate the crack and ensure that it's below that level. And this is part of what I want to discuss under this topic. But if you went to now water tanks made out of reinforced concrete, then the acceptable size of crack reduces to, I think, 0.1 or 0.15 millimeters. Why? Because they use or the consideration or the reason for which we are considering the crack is different. Here we're just saying we are thinking durability, so we're trying to prevent ingress of water and other corrosive elements that might get into the structure. But when it's in water, then we say we are trying to make it watertight. So part of that is we design the crack size to be smaller. Okay, so this is an example of how standards specify the size of the crack depending on the intended use of the concrete element for which we're checking the crack size. These limits generally, for any standards that you pick, would not be limited to just what the standard says. For example, if you found yourself designing a concrete element in, say, in a factory where there will be a lot of fumes of what could be corrosive to chlorine fumes, for example. Some of the things that you would want to do is you want to protect your steel aggressively against these fumes, because the concentrations will be very high. So what you do, probably you would allow for bigger concrete cover than what the standards specify. But also then you could go ahead and say, even the crack sizes in the concrete, I will not just work with 0.25, I will work with 0.1, or I work with 0.15, just to ensure that these fumes do not get to the reinforcement to corrode it. Okay, so these are the thoughts that surround the crack size and why we need to be able, as designers of concrete, to calculate the sizes of the crack. So with those thoughts, I want us to start off by considering this beam. I'm trying to sketch here a 3D shape of a simply supported beam. Not bad. So this beam has got supported here. Of course, we're trying to see the 3D, so let's draw that dotted line there, like that. So, yeah, like that. So this beam supported there and there. Okay. And this beam is, let's assume it's loaded with a point load somewhere in the span there. We know, courtesy of that loading and that arrangement of supports, the top will be under compression. This top will be under compression. And the bottom will be under tension. And because of that tension, we expect that the beam will want to start cracking at the bottom. We want to start cracking at the bottom. And to prevent that cracking, or to take care of the tension there, traditionally we would put reinforcement bars at the bottom. Put reinforcement bars like that at the bottom. So this is from your reinforced concrete design. If we now were to consider the stress distribution, if we were to consider the stress distribution on the cross section of the beam, so we got a cross section. We got the beam there. Why am I drawing bad lines? suppose there's that line there that we call the neutral axis. And this part of the beam is under compression. And then to take care of the tension, we have said, or you have been taught before, that we put reinforcement there. That's, of course, compression and tension. Now, this is only true if this stress distribution is only true if, let me write even the word only true, this stress distribution is only true if the material is perfectly elastic and perfectly isotropic. Okay, so a few words that are used closely to each other. Of course, elastic means this material, we are loading it in a range where stress is proportional to strain, straight line. Stress strain is straight line. Perfectly isotropic means that the material has got the same properties in all directions, has got same properties in all directions. For example, steel is isotropic. Why? Because it has same properties in all directions. If you load it in tension, or if you load it in compression, and you were to plot the stress strain curve, you get about the same curve. I hope you did this in your IBL. Okay, so you get the same curve. When you take the bar, you load it, and take stress strain and draw it, or you take that small sample for compression and you load it until it yields, you plot the stress strain, you get the same. So steel is isotropic. Timber is not isotropic. Its properties in tension, in compression, they're not the same. If you load it against grain or alongside grain, properties are different. So it's not isotropic. The property of the timber material is dependent on the direction in which you are loading. The properties are different in different directions. So that's isotropic. The other term that is close to this, and maybe I can just mention it here for the purpose of maybe your revision or something, is homogeneous. Homogeneous means uniform properties throughout. It's uniform material throughout. Okay. So let's take the example of ugali. So when you make ugali, you want to mix the unga and the water, and to ensure that it's properly mixed everything. Sometimes the ugali has got, you find lumps of flour that has not been mixed with water. You find if somebody has made ugali and they don't know how to make ugali, so you find those lumps. So we say, therefore, the ugali is not homogeneous. If you cut across it, you'll find properly mixed unga with water, cooked, and then you find raw unga that is not mixed with water. So it's not homogeneous. You say the ugali is not homogeneous. But if those balls of unga are not inside, not found inside, but everything is same property. If you cut anywhere, you find it's a properly cooked ugali, then we say it is homogeneous. Approximately, it's never homogeneous, but it's approximately homogeneous. So we approximate concrete to be homogeneous, though it's not homogeneous, because we know there's coarse aggregate from a different parent material, We've got fine aggregate from a different parent material. We've got cement paste, which has got different property, etc, etc. And if you put fibers, you even make the problem even more complex, or the thing more complex. So we only approximate it to be homogeneous. So we are starting with looking at the stress strain diagram and saying this would apply if the material was perfectly elastic and isotropic. So let me write a note here. I'm just leading to the foundational thoughts of how we calculate cracks, so that when we go into the calculation of the cracks, those equations will, or that approach will make sense to you from your strength of materials. That's why I've started from here. So I'll write this note, which covers basically what I've just said. If the beam was perfectly elastic and isotropic, and we had the applied bending moment, the value of the applied bending moment causing the above stress block. We can label this. We can label this section stress block. Cross. The stress at the outermost fiber of the cross section can be calculated using the basic equation this we just borrow it from your strength of materials. Just to remind you that this was the applied moment. Oh, let me move it a bit so that we can label it. This is the applied moment. This is the second moment of area of the cross section. Why is the distance to the fiber of interest? That sigma is the stress at the fiber of interest. Okay. From this equation, we can make M the subject, stress the subject of the formula. So we say sigma, is simply my over I. Ladies and gentlemen, I hope you're following. We've said if we have an element in bending, if that element was perfectly elastic and isotropic, then we can use this equation here. M is equal to, M over I is equal to sigma over Y to give a relationship between the moment, the second moment of area, the stress at a particular fiber that we're interested in, and the distance of that fiber from the neutral axis. Let me add that, from the neutral axis. From the neutral axis. Neutral axis. This equation you dealt with in your strength of materials at some point, probably third year or second year. I can't remember. So using this equation, we can actually find the stress occurring at any point on the cross section. And by extension, therefore, if we wanted to find the stress at that point or at that point, we can find using this equation. If we know the moment and we know the properties of the section, we can find that stress courtesy of that moment. Now, with that thought, I want to push that thought a bit, but we know this. It is fact. Sorry about that. Saying, but we know that the Young's modulus of elasticity, E, stress over strain. And we can remind ourselves where that came from. If you can remember the stress strain curve. Remember the stress strain curve? For example, for mild steel, if we exaggerate it, and we took change in stress over change in strain. So that is stress, that is strain. So change in stress, change in strain. Okay. From that curve, we derived the Young's modulus of elasticity. Now that equation is that equation. Simply stress divided by strain. If that equation is true, if we make strain the subject of a formula, therefore strain, let me write therefore, because we are, therefore, strain is simply stress over Young's modulus of elasticity. And this equation here is the basic principle. This equation is the basic principle for calculation of the crack size in reinforced concrete elements. I will not push this thought further than that today. I'll pause here today, and I'll allow you to, if you have a question on this one, you will ask. But I want to go over what I've just said again, so that you can tie where we are going and where we've come from your strength of material. We said if we have a beam, and if that beam was a perfectly elastic and isotropic material, was made of perfectly elastic and isotropic material, we can draw the stress, the stress block as this one. We can draw the stress block. We know that it will be something like that. If the material was perfectly elastic and isotropic. Now, if that stress block is true, then this equation is true. M over I is equal to sigma over 1, which means, therefore, that sigma, which is the stress at any point on that cross-section courtesy of bending, will simply be equal to bending, the moment, multiplied by the distance of that point from the neutral axis, divided by the second moment of area of that cross-section. Now, if we can find the stress in that manner, which we can, because this one you did in your strength of materials, if we can find the stress in that manner, we can also find the strain by simply using the stress applied and the Young's modulus of elasticity of the material that we are working with. We can find the strain. And I'm suggesting to you that this strain value is the measure of how much the concrete will crack at the surface. This strain value is the measure of how much the concrete will crack at the surface. I want to pause here at this point and allow, if somebody might have a question or a thought that you might want to share with us, please, you're most welcome to do that before we wind up this session. Then in the next session, we will pick these thoughts now and we will do an example, and I'll keep coming back to this theory so that you see in the example what equation ties to this theory or borrows from this theory. Any question, ladies and gentlemen, or any comment, any thought, any concern? Great. So I think we stop here. I'm still asking for some extra sessions. This is really, really interesting. And beyond this, I want to take you through some basic loading of a road structure, like a culvert. That is also very, very interesting. I want to do these two items, and then we close this unit at that point. And both of them are extremely interesting items for you guys to be able to just get a feel of. Any question? Okay, so please, thank you for this session. It was not scheduled, but we've had it. If we can have some more, especially early morning, this is perfect. Thank you very much and have a good morning.